So if you've been following the AI space, you've probably heard these two words pop up a lot: vectorization and embedding. They sound kind of technical, maybe a little intimidating, but they are the key to answering a huge question. How does a machine, a computer, actually learn to understand human language? Well, today, we're going to break it all down, demystify these ideas, and really see how they are the bedrock of modern AI.
So, here's how we're going to tackle this. We'll start with the big problem: why AI struggles with language in the first place. Then we'll look at the first attempt to solve it and why it kind of failed. From there, we'll dive into the breakthrough idea of smarter vectors, how they actually learn what words mean, and see it all in action inside a large language model. Then we'll zoom out for the big picture.
All right, first things first. To get anywhere, we have to understand the fundamental hurdle that AI has with something we do every day: talk.
I mean, this is really the heart of the matter, isn't it? You have a machine that thinks in ones and zeros, in pure logic and math. It doesn't get nuance, it doesn't get jokes, it doesn't get poetry, it gets numbers. So how in the world do you bridge that gap between our rich, messy language and its cold, hard calculator of a brain? Yeah, that's the bottom line. It's that simple. For an AI to do anything with the words you type, those words first have to be translated into the only language it understands, the language of numbers. It's not an option, it's a necessity.
So, what was the first stab at solving this? Well, the initial attempt was pretty logical, actually, and it gave us this core concept called vectorization.
And vectorization is just a fancy word for that exact process we just talked about. It's the act of taking a word, say apple, and turning it into a list of numbers, a vector, that a computer can actually work with.
A really common early method was something called one-hot encoding. Picture a massive list of every single word in the English language. Each word gets its own unique spot on that list. So apple, maybe it's the first word, gets a 1 in the first position and zeros everywhere else. Pear is the second, so it gets a 1 in the second position. Simple, right? Every word has its own unique fingerprint. But this super simple approach has a massive, glaring flaw.
Exactly. You're seeing the problem. According to this math, the connection between apple and pear, two fruits, is literally 0. It's the exact same as the relationship between apple and car. The numbers show no connection at all. And we know that's just not how language works. This total lack of meaning was a huge dead end.
So clearly, we needed something better. To get past this wall of meaninglessness, AI needed a genuine breakthrough. We had to find a way to make these vectors, well, smarter. And this is where the hero of our story comes in: the embedding vector. See, an embedding isn't just a simple on-off switch. It's a much more complex, dense list of numbers that is specially designed to capture the actual meaning and the context of a word.
And boom! This slide is the aha moment. Just look at the difference. On the left, those old vectors, totally separate, no connection. But look at the right. The string of numbers for apple and the string of numbers for pear are suddenly really, really similar. And the numbers for car, totally different. For the first time, the math actually starts to reflect the real world. This was the game changer. A really cool way to think about it is like a giant, multi-dimensional map. We can call it meaning space. These vectors are the coordinates for each word on that map. And words with similar meanings, like apple and pear, get plotted right next to each other. Unrelated words, like car, are way off in a different neighborhood. So now the distance between words actually means something.
Okay, so that probably brings up a question in your mind. How on earth does a computer learn how to create this meaning map? It's not magic. It's actually a fascinating process that's all about learning from tons and tons of data.
It pretty much works like this. An AI model is fed a gigantic amount of text. I mean, think books, Wikipedia, the entire internet. It just reads and reads and reads. As it does, it's not looking for definitions. It's looking for patterns. It's paying attention to which words tend to hang out together. Based on those contextual clues, it starts building that map, assigning coordinates to every word.
So the model starts to notice, hey, the word apple shows up a lot in sentences with words like fruit, sweet, and eat. Then it sees that the word pear also shows up around those exact same words. Over millions of examples, it learns a simple but powerful rule. Words that share the same context probably have similar meanings. So it nudges their vectors, their coordinates on the map, closer and closer together.
Okay, so that's the theory. Now let's get practical. How does this all actually work inside a large language model? You know, the kind of AI powering tools like ChatGPT. So when you type a sentence into the chat box, the very first thing the LLM does is chop it up into smaller pieces, or tokens, basically words. Then, instantly, each of those tokens is swapped out for its powerful embedding vector. Your sentence, "I love apples," is no longer a string of letters. To the AI, it's now a sequence of rich, meaningful lists of numbers that it can finally understand.
And that right there is the key. You have to get this part. This embedding process is the critical first step. It is the gateway that transforms our messy, beautiful, contextual human language into the structured, mathematical information that an AI needs to actually think, reason, and respond.
All right, let's zoom out one last time and tie this all together.
This little table is a perfect summary. Vectorization in general is just turning text into any old numbers. An embedding, though, is a special kind of vectorization that turns text into meaningful numbers. The old way was simple and rule-based, but it couldn't capture relationships. The new way, embedding, is all about learning those relationships so that similar words end up mathematically close.
You know, I think this quote just nails it. It says it all perfectly. Vectorization opens the door, letting our language step into the world of math. But it's the embeddings that walks through that door and fills those empty numbers with all the context, nuance, and meaning that makes language special.
And this is really why modern AI is advancing so quickly. This fundamental ability to represent meaning with math is what lets it understand, reason, and create in ways that are just mind-boggling. And it leaves us with a really exciting question to think about. Now that this foundational piece is in place, what comes next? What new forms of understanding are just around the corner, waiting to be unlocked?